PhD student working with Reddit, and I'm based in Wolfson Center for Mathematical Biology at the University of Oxford. And my research interest is mainly applying these tensor methods to study, simulate, and analyzing the stochastic direction networks. So here I'm going to use the next 1 hour to present some of the results, and I might go a little bit of details into this how tensor method works. So I'm here showing a research cycle, a hypothesis-driven research cycle in system biology. So the cycle is starting from some biology knowledge about some contradiction issues, and then we building the mathematical models, which we have the makes the hypothesis to be computable, and then we perform dry experiments, and we perform system analysis on the models, and if the model predictions is not consistent with the experimental data, then we modify the models. So my work is mostly analyzing these red blocks as dry experiments, and my work is mostly because this box has upstream research, which is modeling, and downstream research is model analysis. So the main purpose when I show that the final goal of the dry experiments is try to maximize the information flow from the modeling to the model analysis. So this is what the tensor method I'm trying to do. So in my talk, I will start with, in my motivation part, I will start with a little bit of introduction about upstream research, which is modeling, and downstream research is parametric analysis or model analysis. Then I will go into some details about how do we perform simulations using tensor methods. And then in example, I will follow this cycle from models to simulations and to model analysis.
Sorry, I have to ask you about the figure. I mean,
yeah.
If this was about like physics in the 20, 30 years ago, I would be like, yeah, okay. But my understanding is in practice, I mean, that biology doesn't go in sort of the sequence of model and experiment unless perhaps you're like one of these biophysics groups like Ray Goldstein or Ben Simons and so forth.
Yeah.
And then in fact what's happening is experiments are going off for their own sakes, and modelers are trying to do everything in parallel. So I see the thing as much more complicated, not as cyclic as that. I'm curious how seriously you take that figure.
Oh yeah, so wow.
Or right, I don't know. Maybe this happens at Oxford.
So no. And then so what I'm really showing is like the three components here. So it's really the main part of this talk. So I'm not working on the left-hand side, the left part of the cycle. So I'm working on the right-hand side. So what I'm really care about is the information flow between these three blocks. So this is okay. So we start with reaction networks. So it is a network that defines the interactions between the different molecular species. So here an example of the reaction network that describing the progression of the cell cycle. So normally when this reaction network is given, under the well-mixed assumptions, we normally have two ways to model the reaction networks: the determinist models and stochastic models. So for determinist models, the main argument is molecular concentrations. So in the models, we write down a set of ODEs, and these ODEs, we integrate these ODEs, and we get a smooth change of molecular concentrations. And under the stochastic context, people are looking at molecular population rather than the molecular concentrations, and the interaction between these molecules are modeled as Poisson events. So the molecular population undergoes a Markov jump process, and if we could simulate this Markov jump process using the Gillespie SSA algorithm, and we get these noisy trajectories. And also we could also using the probability distribution, the evolutional probability distribution of these for the stochastic model can be described by the so-called chemical Monster equation, so which is written at the bottom. So it is a equation describing the changing rate of probability that the system will be in at a particular state equals to the probability inflow minus the probability outflow. So these are the main two types of models for non-spatial modeling of reaction networks. And in recent years, it has been more and more biological evidence to support that, particularly in low number of molecule species, stochastic models have a better prediction than the determinist models. However, in practice, we find people still sticking to the determinist models because the determinist models, the models are far more easy to perform model analysis. So what are the model analysis? So here I present a few of them: the parameter estimation, bifurcation analysis, sensitivity analysis, and robust analysis. So in parameter estimation, and our aim is to really minimize some distance between the model prediction and experimental data such that we can calibrate our model parameters. And in the bifurcation analysis, we try to estimate the qualitative or topological changes in the behavior direction systems. And in sensitivity analysis, we're looking at the quantitative changes. And maybe in the robust analysis, sometimes we're more looking at what the system would behave under the model parameter perturbations. So because if we're working on the simulation side, what our simulation are required to perform these parameter analysis? So is the parameter model predictions means what are the model predictions depending on the model parameters. So for determinist models, the main arguments are mean concentrations. So when we perform the parameter sweeps, so what we usually require is solving the ODE systems, and maybe in the bifurcation analysis, what we need is we don't even need to solve the ODE systems. We're looking at other critical quantities. Or in the stochastic models, we have a few more features looking at, for example, distributions, summary statistics like moments and correlations, and other features in probability distributions like multimodality and or the stochastic observations. And these features are not very easy to estimate in general, especially when we perform parameter sweeps. So, and what we also notice that these properties like distribution or variance or moments or correlations can be estimated or derived from the probability distribution. So a naive way to perform the parameter analysis simulation for the parameter analysis of stochastic models is using this brute force way of computing it. We start with model equation, which is a chemical master equation or chemical Fokker-Plan equation. We solve that equation automatically, directly for a range of parameter values, and we get this conditional probability. And after we obtain this conditional probability, we post-process this probability to the model feature that we were interested in. So this is sort of a brute force way to compute, to perform simulations to conduct the parameter analysis. However, in practice, no one really do perform simulation this way. The reason behind this is because when we play around with this conditional probability, is actually, well, we will incur the so-called curse of dimensionality. It means we call the curse of dimensionality refers to the phenomenon that in numerical computations where the complexity and the storage requirements grows exponentially with the number of parameters. So here's a bit of a sense about what the curse of dimensionality means in practice. So if you have one-dimensional problems, and in each dimension we discretize by 2 to the power of 10 nodes, which is like 1024 nodes, the storage requirement is only 10 KB. And if it goes to two-dimension problems, the storage requirement to store the solution will be 8 megabytes. And 3-dimension, you've got 10 megabytes, and 4-dimension we're going to be 10 GB. So this is one kind of, here is only the storage that we will have to deal with when we if we want to address this probability distribution. So in order to get around this curse of dimensionality, what is
1,000 or 2 to the 10th power representing here? Is that just
so here's a non-zero number of non-zero elements. So it means like how many grid points we put in each of the dimensions.
Okay.
Yeah. So this is like so one dimension is just n to the power of 1, n to square, n cube.
So this is kind of the dimension of the state spaces.
Yeah. I mean any space, like maybe the state space and the parameter space. So because if we were looking at this probability distribution, like we have both state space and parameter space. So what happens in practice, so the most existing method what people are doing is rather than dealing with model equations, people are dealing with using stochastic simulation algorithms. So we start with Gillespie simulates A or chemical non-trivial equation or top leaping methods. We perform the stochastic simulations and get the time trajectories of the model, and then we're post-processing these trajectories and obtain this model features we wish. So in this way, this Monte Carlo method is quite a success that we can lift the curse of dimensionality in the state space, means the numbers like molecular populations. However, there's still one problem exists there, is the parameter space. So when we have a large amount of parameters, and what we need to do is we have to repeat this whole process once and once again for different parameters, for parameter values. And if the parameter value, the number of parameters are large, and the time we need to repeat the process grows exponentially as well. So the tensor method I'm going to show today is we're going back to this original, the natural way of performing the simulation. We're going from the model equations, and then we compute the conditional probability for both for the state space and the parameter space, and we're post-processing this probability and get the features we wish. So then it's so a bit of background about what tensor is. So first, the tensor is just a terminology that we usually use to refer to the multidimensional array. So this is not the same terminology that we usually use in the physics, or like a tensor stress or tensor field. It's just a way to say the multidimensional array. So the order of a tensor is a number of the dimensions. So the zeroth order tensor is a scalar. A first order tensor is a vector. A second order tensor is a matrix. And then also we have higher order tensors. And
why do you say that it's not the same as physics and engineering? In like general relativity, you have these tensors with 4 indices. Isn't that just the same thing what you're talking about?
Yeah, on the mathematical level, it's the same. But I mean, people, when we're talking about tensor, people usually think about the forces. But here we mostly deal with the multidimensional data.
I mean, I think with the examples you're talking about, stress tensor and so forth, I mean, that's just a matrix function. It's just a case of a tensor with 2 indices, right?
Yeah. Okay, so when we talk about tensor decomposition, the tensor decomposition refers to general procedure that we decompose a higher order tensor into one-dimensional components, which we're going to show one example later. And so this fundamentally, the tensor decomposition is a way we do data compression. So how could it be applied in our problem? So you're gonna be, in our problem, we got first solve the model equation, which could be master equation or focal point equation, simultaneous for range of parameters. So first the task is solve the equation, then you're gonna store the whole solution, which is full solution, and third, you're gonna post-process the solution for conduct the parameter analysis. So the idea behind this is because so we think about the tensor decomposition is a data compression. It's like in our daily life, when we have a big file and you want to email to another person, what you normally do is put in the zip file and upload to the email and send another person. So the tensor, so this is where the data compression is usually made. This is based on the fact that the original data, original file can be opened, can be stored. So the tensor method works in a way that everything starts from a zip file, everything starts from the data that has been already compressed. So you write things based on the compressed data, and you send things, you work with the compressed data, and you open things with compressed. Everything's this. So yeah.
Is the compression lossless or lossy?
What do you mean?
Is the compression lossless or lossy?
It is. There are some approximations I'm going to show later. Yeah. So okay. So yeah. So what the tensor method really, the idea behind this, because we want to use this data compression techniques to perform everything based on the compressed version rather than the full version. So before I introduce the method, let me introduce this network representation of the numerical linear algebra, which the nodes determine the tensors, and the number of edges that connects to the nodes determine the orders or the number of dimensions. So the scalar is just a node, a vector is a node with connected with one edge or one line. This is a matrix. And when we perform algebra operations, we could do, we connect the three edges, then we got this one. So the connected edge means we have to multiply the corresponding elements, and we're summing up the corresponding indices. And all the matrix by matrix builder can be represented this way. It's just a different way to visualize the linear algebra operations.
So, can I add something?
Yes.
So when you have a free edge, that's a vector. When you have two free edges, the end thing is a
matrix.
Is a matrix.
This is how many indices are there to denote the
and the circle tells you how many indices.
Yeah.
Okay.
So first we're going to describe how we're going to do decomposition in two-dimensional case, and later we're going to extend the case to higher dimensions. In two-dimensional case, suppose we have a matrix which is X, and we could perform singular value decomposition and make it as a product of a left singular matrix, which is U, and right singular matrix, which is V, and the diagonal matrix, sigma. So the diagonal elements are the singular values. So we could truncate this. We could truncate the SVD and get a smaller size based on the size of the singular values. So this is called the truncated singular value decomposition. And what also worth to mention that it's an equivalent form to writing this way. So here is singular value decomposition, and here we can write it as a weighted sum of order products of the left singular vector and right singular vectors. So these are sigma 1, 2, 3 are the singular values, and U1, U2, and UR are the column vectors of the left singular matrices, and then V1, V2, VR are the row vectors of the V matrices. So in this way, I could write a two-dimensional matrix into a sum of one-dimensional components. So in this way, the complexity is reduced from n squared to 2 times n times r. So we have additional parameter, which is r, which we usually call it rank. And this truncation is based on SVD, so it's quite stable for computer to run. And next, we're gonna extend this decomposition to higher dimensions. So this is one example. We usually call it tensor train. If people work in numerical analysis, or density matrix renormalization group, or matrix per state, if you're working in physics or quantum mechanics. So we start with a four-dimensional tensor, which is four-dimensional data cube. We reshape it into a matrix where the first dimension, the row indices correspond to the first dimension, and the column indices correspond to the rest of the three dimensions. And we perform matrix SVD decomposition, and we get the left singular matrix out. So the left singular matrix, it actually contains the information in the first dimension, and this bridging dimension we call it rank. And then we take x2 and reshape x2 such that the row indices contain the second dimension and the bridging dimension, and put the rest of the three dimensions as the column indices. We perform matrix SVD in this way, and we take the second dimension out. So second dimension contains the two bridging dimensions and its original dimension. And then we take x3, we perform the same procedure, and we take the third and fourth dimension out. So in this way, a full format of the fourth order tensor is decomposed into these train structures. And the storage requirement for this train structure is only grows linear with a number of dimensions if these bridging dimensions are relatively small. And also we can, of course, we can, I mean, it depends how we are using this SVD decomposition. We can also get other tensor decomposition, which is like this, which we call it Tucker decomposition, or we could decompose in a tree structure, or we can decompose into like a network structure. So the reason I'm presenting here is not because in practice we are going to, from this full tensor into a decomposed like tensor train representation. It's because we want to build a connection between the original data and the data that we are going to store on the computer. So this, so this is like, so this can be considered in this way. So originally we have a problem where all the unknowns, the X denotes unknowns in the system. But the point is, if we find a way that we can store these solutions in a more efficient ways, we don't need to compute all the elements in X. We just need to compute what's going on in these one-dimensional objects. So this is where the model reduction is performed. So originally we have a big problem, which has a full, which has a cursive dimensionality, and we have hypotheses that the solution can be efficiently represented in this tensor train format. Then we can somehow rewrite the model equation such that we always find the equation in this form. So we totally get rid of the exponential scaling in the problems.
But you are making an assumption that, for example, the sum of the singular values are very close to zero, so that kind of makes sense.
So that's a key assumption that's been made in all the tensor method is solution can be efficiently being stored in this way.
Okay.
So and in practice we do find that many solutions can be approximated in this way very efficiently.
So when you say in practice, you mean when you actually solve it?
When I actually solve the system, we find the solution can be the R's here, R's are the ranks are relatively small.
Okay.
Yeah.
If you had a problem where that assumption was not true,
Yeah. So
but you still solved it using this, what happens? Is it obvious that something went wrong, or is it not obvious?
I mean, so what happens if the assumption is wrong? I'm gonna show later, right? Even the assumption is right, we have some problems. If the assumption is wrong, what is gonna happen is maybe starting an initial guess, which is R really small, and as the program progresses, the R increases, and then the storage blows up, and the simulation is killed. Yeah.
So there's some adaptivity as you go along on changing R. And
Yeah.
So there's some sort of internal check that actually the SVD kind of idea that singular values are small enough, so you're not losing much by throwing stuff away. In some sense, is that what you're saying?
No. I mean, what am I? So can I say again?
So you said in your program you kind of you start with a small rank and you kind of update it.
Yeah.
But so if that was kind of a reasonable thing to do, the algorithm at some point will just stop updating R.
Yeah. So the R is updating all the time. So I'm gonna show you later.
Okay.
R, I mean, yeah. So here we only show that this is how the solution gonna be represented in this way. But so next one gonna show is how gonna find the items or the numbers in each of these tensors. We call it tensor calls, and this called the ranks. So in order to do this, I mean, previously we have shown the vectors, right? The vectors can be efficiently stored in this way. And now, next we have to define the operators. Operators in numerical algebra, there's just matrices. And because matrices have two indices, one for the row indices and one for the column indices, so we can write the corresponding tensor train decomposition for the matrix in this way. So for each dimension, we have one row indices and one column indices. And the way we perform numerical linear algebra can be performed this way. We just connect the free edges in the corresponding dimension. That means, so what the operation we need is really multiplying the elements and summing up elements in the corresponding dimension. So the total complexity by performing this matrix by vector, similarly matrix by matrix product, is grows linearly with number of dimensions. And if you're looking at the two nodes in this red circle can be combined in a single one, this is to say, so the products also in the same format as we had. And the problem is the ranks are multiplied. So these ranks are multiplied. Well, we don't want that because ranks also control the storage. So the difference between the tensor linear algebra here and the original, our traditional linear algebra is tensor linear algebra becomes a lot cheaper when we perform these operations. But after each operation, the storage increases. So we have to then perform SVD-based compression to compress the storage to reduce these ranks. So this is the main difference between we will perform linear algebra, in the tensor train format and in the standard vector matrix format. So once we set up the tensor train representation for the matrices, now I'm going to show how to put the models into the matrix form. So then here I'm showing I'm using the chemical Fourier equation. So this is a diffusion approximation of the chemical master equation. And the reason I'm using that is twofold. First, the chemical focal point creation is more analytically tractable. So, and also when we're doing, and second, numerically, when we discretize this equation, we have a lot more freedoms to determine what the grid size are, so we can somehow decide what the size of the system. So it's, whereas in chemical master equation, the grid size is fixed to integers. So here I'm writing the stationary equation directly. So the LFP denotes a focal point operator, and a PX is a stationary distribution, and right hand side is 0. And this operator equals to the divergence of the flux, where the flux is defined as, and V is the drift vector, and V is the drift vector, and D is diffusion matrix. So from the simulation perspective, we want to discretize this equation, and what we really need, if we use finite difference method, what we really need is discretizing this propensity functions, as well as describing the derivatives in there. So for the propensity functions, if the reaction system is a mass reaction system, so the propensity function is naturally separated into different dimensions, right? So we usually have a product form, x1 times x2, or x1 times x1 minus 1, so they are naturally in a separate form. So here I'm showing, below I'm showing all the derivatives. If we discretize the finite differences method, we can also have a separated form. So for example, if we want to take the derivative of high-dimensional objects with respect to x1, and the separated form is looking at the C here denotes the central difference, and I is identity matrix, and this product means the quantum product or tensor product. So if we multiply these one-dimensional matrices in this way, it as a whole is going to work as the derivatives. And also we can define the similar for second derivatives and mixed derivatives. So I'm here showing that all the state space can be discretized. The operator that the state space can be discretized or constructed using only one-dimensional operators. And then we progress to parametric chemical focal point operator, where here now, previously, we consider the parameters as constant. Now we're looking at, now in this equation, we explicitly write k parameters as variables. So now this equation not only have n-dimensional state space, we have m-dimensional parameter space. And then we just reorganize the term. On the mathematical level, the operator are the same, but we all reorganize the operator such that we can factor out all the parameters in this way. And once we've done that, we can show the tensor structure of this operator, if you use the finite difference method, can be have this form. So here L1, L2, L3, Lm are the discretization, finite difference discretization of the sub-operators. And we have shown before these sub-operators can be, this contains the state space, which can be constructed using one-dimensional matrices. And the K1, K2, K3 till Km are diagonal matrices, where the diagonal values only corresponds to the nodal values of the parameter values. So these are the separate one-dimensional matrices. If you put them together, the whole operator is a discrete version of the operator which is shown here. And here, so this includes both state space, which is in L1, discrete like this, and the K1, K2, K3, which is state space.
Sorry, so these are operators acting on some other tensors, or what are these operators going to act on?
So these gonna act. So this is a sort of it doesn't really matter. So if you discretize the equation, what you normally do is no matter what dimension you have, you're going to have a very long vector which is put it there.
Right.
So the finite difference method, you're gonna have a huge matrix.
Yeah.
Which
I understand on the left-hand side kind of what's happening, but I'm confused on the right-hand side where it seems like now you've got, what's going on in the first component that it gets all the L's, right? And then you start with K1 at the second component. I'm getting confused. What are the m+1 components of the tensor? Your tensor structure, you've got, what's special about the first index of the tensor that it gets all the L's?
Okay, so all the L's, these are the L's are finite difference discretization of the operator, which only contains K1s. So if we connect all all the terms in here, you know, and factor out K1. This operator is the only, L is a finite difference operator of discrete type in this one.
But why is it operating on the first index?
Oh, this is, you could rearrange. I mean, the order doesn't really make a difference.
But isn't it, I mean, sorry, isn't J essentially, now you have J M parameters and J is the index referring to the parameter.
Yeah, J is.
So it's not dimensions, I think it's parameters.
Yeah, so why is it m plus 1? What's the other 1? Is that space? Oh, I see. So your L's are going to be sort of themselves tensors that you got from the left-hand side.
Where
Is that the point?
Where is n plus 1?
Well, I mean, you've got, you have m circles with crosses in them between the components, right? Because you're going from K1 up to Km along some diagonal, right? That's m entries. And then you have
here's
one
an
in front
n
of that,
entries, yes.
right? And then, that's what I'm saying, you've got m plus 1 things tensor together, right?
Okay, yeah. So here is L1 is itself is an n-dimensional thing. So n is L1 is n-dimensional things, and K1 and these are m-dimensional state. So these are the parameter space, and these are state space.
Okay.
And the space space has been, this can be discretized in this way. So the L1, L2, L3 can be constructed using these parameters, these operators, and these are the m parameter space.
And so those L's are themselves tensors that are like.
Yeah, so these L's have, itself has some separated
Yep,
form we
okay.
constructed by this one. Okay.
Excuse me. Another question. Do you assume that the Fokker-Planck operator can be written down as a linear combination of the parameters?
Yes,
Because
it's assumed. Yes, it's assumed. But I mean,
Because in general,
it's because for the chemical Fokker-Planck operation, it is. So
no, okay, fine.
Yeah.
In general, it might be different.
yeah, in general it might be different.
That's a strong assumption in general.
But
for
if,
chemical,
as now, I
okay.
mean,
Yeah, okay. Fine.
even in the case where you can have K1 times K2, so you can
Yes,
still
but
get around with.
for this structure to work, you need that linear.
Yeah, but I mean, you can slightly change the structure, then you make that works as well. So for example, you have K1 times K2 here, so you just K1 put it here, you multiply a K1 matrix here as well. So as long as it's just it's a product form, you can always put it this way.
But in chemical reaction networks, it's always linear, isn't it? Or am I
Yeah,
mistaken?
in that case, okay.
And that was the initial condition, right? So if the parameter was the initial condition of species, concentration species.
What I mean by parameters in each condition.
If the parameter K was the initial condition of your concentration, your modeling wouldn't appear as a linear combination.
Yeah. Well, yeah.
So even the initial condition has to be like this.
But in that case, I mean, the parameter doesn't make a difference because I'm solving a stationary.
Are you solving
Stationary. We go straight for the stationary equation rather than. Yeah. So now we can proceed. So I've got theories. So once we put it this way, then this theory really says, okay, we have constructed, we have used only one-dimensional matrices to construct the high-dimensional operators, and then we put in the train format, the tensor ranks is bounded by this value, which is 1 over 2n, which is the number of parameters, n is a number of chemical species. So this referring to the fact that there's a tensor train format to store the whole operator that includes the states and parameter space will grow at most cubically with the number of chemical species and quadratically with the number of parameters. And in practice, it's actually smaller because we can, after we have constructed, we can always use the singular vector compositions to even truncate the ranks to get the approximated operator.
But can I ask something? What is the assumption then? Is it? I mean,
So here
is it just because? Sorry, I mean, so is it because things are mass action form that tells you something about the singular values that allows you to do that?
No. So here is all constructed. So previously, so what I'm showing here is we're going from a high dimensional things and we perform SVD to get this one. What I'm showing here is the operator itself is just can be written this way. So itself is just
Already.
there's no assumption there. It can be put in this way if we discretize using finite differences method, and it was as well as the finite element method. So this is constructed. It's not from a high-dimensional object and approximate to low-dimensional object. I mean, show you and complete the structure. I'm not, you know.
So you're somehow saying that there is no approximation, so you're not throwing away.
Yeah. So here in terms of operator, I'm not throwing away the things. So in terms of operator, it's just stay as it is.
When it does SVD.
Yeah. So approximation will come later. So if we have this estimation, then if I'm not very happy with this estimate, then we perform truncation of this ranks. Then we have that's where the approximations have. But at this moment, I'm showing what I should theoretically be put in each of these boxes.
So can you go back? Sorry, I'm just trying to understand. Can you to the theorem? So if I had, I mean, if that was just the two-dimensional diffusion equation, I mean, maybe I don't fully understand what this thing is saying. But if I had the two-dimensional diffusion equation and I was discretizing it,
yeah,
then I would need a matrix of size n squared. Yeah, I mean, if I was doing it naively. So what I mean.
So if you have one-dimensional,
Let's assume we had a two-dimensional and I had n points at each thing. So I would have my matrix, yeah,
yes,
in the way that I will do it naively, would be n squared by n squared.
yes, that's what n squared by n squared.
And
so,
what are you saying there, basically? That you can do it with less than.
So here, so if you diffusion equation that we take away n. So let's
Yes,
say n is so maybe let's set n equals to 1. So what I have saying here is if in the full map here n is number of dimension there. So here
N is 2.
n is 2, right?
Yeah.
So what I'm saying here is if we're using tensor train format, it goes in, if you set n equals to 1, you have n times small times n tap to n cube.
So just to understand, so this thing basically saying that if you had the diffusion equation and you're trying and you're doing the naive thing of finite differencing and not using the tensor train format,
yeah,
you would have to store O n to the 4, while if you're doing like this,
yeah,
you would have to store n to the 3.
n times 8. So this is a sort of with each dimension you put small n number of nodes. So you have small n to the power of 4.
Yes,
And here you have small n times 8. So this is where the exponential scaling in the full format, and here is sort of not exponential scaling, it's a cubic scaling in terms of the number of dimensions. So n is the number of dimension here in your case. Okay, so it's here so it's n times 8. Okay, so we finally arrived this, which is so we want to compute the steady state distribution of the computer focal point equation, and this gonna end up with this principal eigenfunction problems in the Newton algebra. So A is what we have shown before, is a discrete Fokker-Planck operator which contains n plus n dimensions, but it's stored in the tensor train format. And X is a solution we try to compute, and lambda 1 is a principal eigenvalue which have the smallest magnitude, I mean close to 0. So if it's in the traditional method, there's many ways to compute this thing. But however, in tensors, we are sort of limited because we can't. It's very hard for the tensor to manipulate each element in the high-dimensional tensor. We normally deal with dimensions. If we operate something, we operate everything in certain dimensions. So we gotta use this inverse power method to solve this eigenvalue problem. So this the method starts with approximation of this principal eigenvalue and an initial guess x0, and then we iterate solve this linear system, and we rescale the solution and we solve this again. So what
How do you update sigma?
Sigma is a shift.
Do you update it or do you bother?
At this moment, it's a constant.
Right.
So it's a constant. So the convergence rate of this whole algorithm to the final principal eigenfunction is a sigma times lambda 1, which is the smallest one, and the second smallest one. So because we know all the eigenvalues are negative, And then we can always choose a positive sigma such that eventually can converge what we want. And the difference between this one has become, this algorithm has been proposed for quite many years, and it has been used mostly using the traditional matrix and vector methods. But here, we keep all the elements in the same format, the tensor separated format. So that means to say we have to solve this linear equation using the tensor method. So I'm showing you how we're gonna solve linear equations here. So suppose we have a linear equation ax to b, a, x, b are all in the tensor format. And then what we normally do is define an objective function which which is a norms, which can write it this way. And then we do so the solution of this linear system is the minimizer of this objective function. And this objective function this problem is convex only when the matrix A is symmetrically positive definite. So I'm going back to this point later. So this is a high dimension optimization problem, which is very complex to do. So what we normally do is taking this greedy approach. We do optimization. We could do optimization dimensions by dimensions and alternating between dimensions. So we can go one step, another step, another step. And if the computation power allows, we can do 2 dimensions at a time. We can go from here to here to here to here. So this implies if we have this solution initial guess already being represented in this tensor trim form, what we can do is minimize this objective function by only manipulating the elements there in the first 2 dimensions. Then, while keep all the rest of the dimension as assuming it's already optimized, then we'll progress to the 2nd and 3rd dimension, and we progress this way, and we do the sweeps. We call DRNG sweeps. And in this way, if matrix A is positive symmetry definite, and then this one you can eventually converge to the solution of this linear system. However, the problem is we don't have this symmetry. If you go back here is a Fokker-Plot operator and minus a identity matrix. This is not symmetry positive definite. So here's the problem. I mean, it's likely that we may not get this solution right. So the point, so the trick here is we don't need a global optimizer to really come to make the solution take us to the steady state solution. So so we have outer iteration, which is the inverse power method, and at the same time we have inner iterations. The inner iteration is what we do the optimization on the tensor level. So each outer iteration we sort of redefine a optimization surface, and this surface can have local minimums. So if we don't get the initial condition quite right, and we may get trumped into the local minimum. So, but it also if we take this this function with respect to the solution, we see the gradient is given this way, and the gradient is approximately 0 if we let x k plus 1 equals to the previous solution if the sigma is large. That is to say, so if we choose a very large sigma, our solution for the next iteration will be very much close to the previous solutions. So what is this is sort of telling us if we always put the initial guess to be the solution of the previous step, and I can choose a sufficient large sigma, we can always moving the surface slowly, that we can make sure that I'm always somehow in the basin of the global attractor rather than in the local attractor. So this is how we control that using a local optimizer to get the solution all the way to the steady state solution. And so here's an example. I'm showing you an example. It's a 50-dimensional reaction chain. So this S1, S2 represent the species, and K1 to K102 are the parameters, and I fix this parameter as constant. So I'm solving a chemical Fokker-Plot equation with only the state space, and the number of dimensions is equal to 50. And for each state space, I use 2 to the power 7 is approximately 100 nodes. And if we want to store the solution in the full format, it's gonna be 10 to the power of 105. However, if you do that in the resulting tensor, final solution in tensor is only about 10 to the power of 5. And the computation time is quite huge. So here's the solution, what a solution looks like. And this is what I computed. I'm choosing this networks because this one, because it's only have monomolecular reactions, so we have analytical solutions for the margin distributions. So I can compute them. We can compare the analytical solution with the solution I've computed. So we see that all the dimensions, the 50 dimension, are sort of in a similar accuracy. And here is a arrow. So this is how the arrow converges with respect to the computation time, which is a black curve. And what I'm showing here is the tensor ranks, how the tensor ranks evolve over the simulations. So what we're showing here is once we start an initial guess, of course we're gonna choose an initial guess with very low tensor rank. But what happens is the tensor rank blows up to very high value, and it takes very long time just to get a very bit of the error decrease in the arrow. Then slowly the tensor rank decreases. So what I show here, we can guarantee the initial condition have low rank, and we can also make a hypothesis that the final solution is rank, but we can't guarantee that the intermediate solution has the low rank. So this is.
Can I ask a question? So the discretized chemical Fokker-Planck equation has a one-dimensional null space, which is the thing that we want to find. It gives us the stationary distribution. So when you make this approximation with a lower rank tensor, you increase the size of the null space. So how do you know that the null space you find is the true null space, the one that you want, rather than the one that you've created through your approximation?
If I discretize it, it's still the null space is still one dimension, right?
But you're approximating this thing which has nearly full rank. It's got a one-dimensional null space by something which has got a bigger null space because you have.
Okay,
it's
so
approximating it by lower rank.
That's where it goes back to where we have just discussed. The operator, the way we construct operator is exact. So we don't do approximation on the operators.
So this thing with the changing rank, what's the rank?
The ranks is a solution. So this ranks I'm showing here are the solutions. So the operator can always stay the same.
Okay,
right?
so you're approximating the solution by a low rank thing, not the operator.
Yeah, not operator. So this is gonna be So this is how the solution ranks grows over time. So this is sort of one of the key challenges in tensor methods that we may have at this moment is we can have a very nice initial condition, and we can find the condition can be stored, and we have a lot of data compression ratios in the final solution. But the problem is the optimization path, we go from the initial state to the final state, it might blows up, and this might kill the computation totally. But in many cases, sometimes we can this growth can be tolerable, so eventually we're gonna have a very low rank solution. So now we gonna
but if it goes quite high up, don't you kind of run the risk of?
Yeah, if it goes high up, they just kill the simulation.
So if it do you run the risk of sort of like running out of memory or something? That? But I guess you couldn't do it in any case at the first place, so you might as well try.
Yeah. So what because in practice, what normally happens happens in quite an early stage of the simulation. So once you put the coding and let it run and see how the ranks grows, and if it grows very high, it's just you're never gonna make it. So just stop the simulation. Yes.
You may have said this, I just want to make sure. You're comparing to the stationary distribution of the jump process,
Yes.
not the diffusion process.
The jump process. So because I'm choosing, so here's the molecule.
But you're
number.
working on the diffusion process.
Yeah. But because I'm choosing quite high molecular numbers, so this.
I just wanted to make sure.
Yeah. So we can quickly go through the function analysis. So maybe it's a bit of, and it's more here to illustrate how the tensor method works with the example. But with most of the dimensions are all state space. But I could freely allocate 25 dimensions to be the state space and another 25 space to be the parameter space. In that way, we could perform the parameter strips. And here's a few examples. So for example, in the parameter estimation, so here I'm showing an example of a moment matching inference, where we try to minimize distance measure that is a weighted sum of the empirical moments and the model predictions. So So the minimizer of this distance measure would be the estimate parameters. And from the computation level, what we really need to do is perform this high-dimensional integration. So I suppose we have already got the solution computed, this conditional probability computed in this way, where X is the state space and K1, K2, K3, K4 are the parameter space. So to compute this integral, we just need to multiply it by a vector to this dimension, and then this whole thing is going to left with the moments, which is four-dimensional space, because that corresponding to different combination of parameter values. And then here's an example of Shuohao system, which a system has one species and 4 parameters, and this is then I perform solving the corresponding focal point equation, which is a 5 dimensions, and I sample the 4-dimensional space, and using 10 to the power of 8 samples, and total simulation time is 30 seconds. And if we divide the total simulation time by the number of parameter samples, it's gonna be on the level of 10 to the -6 seconds per parameter. So this would be a lot more efficient than if we compute parameter sweeps, parameter by parameter. And then here I'm showing you just a surface of what the distance measure looks like. And also we could perform bifurcation analysis, sensitivity analysis. So here I'm showing an example of a cell cycle model by Tyson. And this model is have 6 different forms of chemical species. And the one I put this K1 as a bifurcation parameter. So the total problem in this problem is 7 dimensions. And what I'm showing here is the margin distribution corresponding to different parameter values. So here, the first row corresponds to the first 3 chemical species, and the second row corresponds to the second chemical species. And what we show that for the different parameter values, we show that in the first 3 state space, we have this oscillation tube, and for the other 3 dimensions, we have this bistable oscillations. And also, we can do the sensitivity analysis. The way we do sensitivity analysis is often using a finite difference, and the S denotes a sensitivity indicator, and we use theta to refer to some certain observable quantities, and because we compute the probability distribution, so we have lots of freedoms to choose what observable quantity we want to compute this in the theta. So what I'm showing here is so here the blue lines, okay, that corresponding to the sensitivity where the theta equals the probability distribution, and here the red lines corresponds to the oscillation amplitude, and the yellow lines corresponds to the average behavior or the mean value. So and this become I think it's to mention here because normally we have problem in the Monte Carlo method is that when we do this finite difference, this arrow increases dramatically when the delta k decreases, is small. Whereas in Tensor method, actually in benefit from smaller delta k, because the smaller delta k is, the solution gets more close to each other. Then we have, because the solution are more alike to each other, we have smaller ranks in the solution. And finally, it's a robust analysis. And the robust analysis so what we compute in the model is this conditional probability, is the intrinsic distributions. And in practice, we could also assume some parametric distribution, which is denoted by BPK. And then we could compute a combined distribution using this high-dimension integral. And we have shown that by doing this high-dimension integral is quite efficient in the tensor format. So, and the complexity of doing that grows linearly with number of parameters in the system. And here's this example, which is a neural excitation model where the x1 there's a positive feedback on the x1 and the negative feedback through x2 back to x1. So in this model, we have 2 chemical species, x1, x2, and the 4 model parameters denoted here. As said before, we sample the parameter space and we simulate the parametric chemical focal point equation. So what I'm showing here is the distribution where the parametric distribution is only delta distributed. That means there's no extrinsic noise in the system. And here is a distribution where we have Gaussian noise in the parameters. And what we show here we have a clear oscillation path from the low state to higher state. But here the path is is somehow changed. So this might be the case where we might observe in a group of cells, and this might be we could observe in a single cell. Okay, to sum up, we have presented a tensor-based framework to perform simulation and analysis of the interaction networks. We call it TPA. And this TPA can be divided into 2 steps. The first step is computation, and second step is analysis. So in the computation, we simulate the steady-state distribution simultaneously for all possible parameter combination within a parameter space and store the solution into a tensor format. And then, using the resulting tensor data, the tensor data are analyzed using the tensor algebra operations, which the computational complexity scales linearly with the number of dimensions. So the work has been presented also have a toolbox which is available in this website. So these are, at this moment, the website is only some template code. It's not yet a well-developed toolbox. So the future plans. So it'll be interesting to see, because to have developed tensor networks rather than tensor training. So it's good to see what can happen if we have developed tensor networks that are topologically equivalent to interaction networks. And also, I'm planning to extend these ideas in the context of the spatial stochastic models. Okay, finally, I would thank my supervisor Radek and my collaborator Thomas, who is also working on this tensor method, and he's going to give a talk in April conference on a similar topic, and Andrew and Raman for their work in analyzing the chemical focal plane creation, and then supported by European Research Council studentship. Okay, thank you.
So can you go back to your theorem again? So I'm looking at these results with the eyes of someone who's trying to apply, say, a diffusion, a differentiation matrix to a vector. Say I'm trying to compute the Laplacian applied to a vector, right? I'm trying to compute Laplace of U. So you mentioned here the orders of magnitude for storage formats. But what happens in terms of matrix vector multiplications, which I think
matrix vector multiplications. So this is where it is matrix vector, right?
Yeah. So do those estimates hold?
Yes. Yeah. So,
but then wouldn't these mean that we should stop using the sparse format used by MATLAB and we should instead use your sort of matrix vector strategy instead?
Okay. So
if you scroll back to the theorem, right? So at the moment, if I declare a matrix as sparse in MATLAB, that's what it's being done, right? I mean, I shouldn't, in the first place, even declare it as full.
Yeah.
Are you now telling us that instead, if we use the tensor format, we would get that performance on a matrix vector multiplication with the Laplacian in 2D?
Yeah. So the difference between So in terms of storage, I have to say we could really this one, the tensor method, really have advantage over the existing sparse matrix format. But the problem is because when we have performed, we got advantage in performing this product, but the result is we have the storage of the matrix matrix product is not fixed. What I mean is we might have this vector and we have the matrix, but when we multiply it, we have a different storage for the resulting vector. This is what I mean. So in the sparse matrix format, we have a matrix by matrix, and the storage is sort of fixed. The order is fixed.
Yeah.
But when we perform this way, the storage is not fixed. For different vectors, we can have different storage requirements. For different matrices, we have different matrix requirements. So we have to really perform this.
Why, if the vector is full, you're going to have different storage requirements? So I'm taking the Laplacian is fixed there, right?
Yeah.
So if I now apply the Laplacian to a given vector, why would I have different storage requirements?
No, not for the traditional matrices and vectors.
Yeah.
So you will always keep a vector always equals to n, right?
Yeah.
So, but what happens because of the way we store the vector is this way. So, and the storage grows with the bridging dimensions, and this bridging dimension is not really clear what the bridging dimension would be for the resulting vector. So yeah.
So does not your iterate, your power method sort of rely on matrix vector multiplications.
Yes, it also relies on matrix multiplications.
And so you're telling us that matrix vector multiplications are not as advantageous to do.
So the matrix are, no. I mean, very high dimension, it does. It does, I mean, in terms of the way we compute the matrix and vector product. But just after each operation, we need to perform a compression.
Yeah, okay, I was interested in the non-compression case.
Yeah, so it was just, the difference is because previously we do the algebra operation, then we go to the next algebra operation. But here, in between, after each algebra operation, we do the truncation, we do approximation.
Sure.
So it's sort of, so basically, in what it happens in computer is we make a very small perturbation to each of the operation we do. But here we can slightly bigger because we use this compression techniques. Yes.
So you said that you had to use power method essentially because it was simple. So what was the reason you couldn't use Cradle methods or Arnoldi to compute the eigenvalue?
So the creative method, I did use it before. So what happened is, so if you're looking at the method, it doesn't rely very much on the matrix and the numerical algebra. It doesn't really have lots of matrix plus matrix time vectors. So as I just said, the more intermediate vectors I have, more risk I'm gonna have. Some vectors blows up to some blows up the storage and just kill the simulation. So in this way, actually, the only need is to solve the linear system, and this way. So I don't need to do too many matrix vector product, which grows. Yeah.
And what value do you use for the shift? Because obviously you're looking for the 0th eigenvector.
Yeah. So
do you
the
just
shift
use
is
0 or do you use?
So I mean, so this is basically the where I'm talking about shifts. So I'm actively choosing the shift. So when I find and my algorithm converge very slow, I always choose a bigger shift, such that make the next reaction closer to the solution of the solution of the system closer to the solution of the previous solution, previous iterations. So this shift is adaptive choosing.
Right,
so that's why I call it a black box solver.
Right. Okay. So I always thought that the shift, it was a good idea to put in the value that you knew. So it's not the optimal value of the shift is not the value of the eigenvalue that you're actually trying to find the vector for.
Yeah. So
Right.
no. So what I'm here is because the convergence rate is equal to this, and all these number one, number two are negative. So I just making sure that I choose a shift that this one is smaller than 1. Then I'm guaranteed that the algorithm always converges, right? So these are negative, so I could always choose a positive shift, no matter how big it is. I mean, a bigger, I have a smaller convergence rate, but I'm more likely, go into the fall into the basin of the global attractor rather than a local attractor.
When you say convergence rate, it's an exponential of rate, an exponential convergence of this rate. That's it.
So the convergence rate is like how many times you do each rate. So it's actually the k power of k. Yeah.
It's geometrically it has this rate.
Any more questions or comments?
So I understand it's not exactly what you're doing here, but in principle, so for a high dimensional solution, have you considered using this technique to directly go for the adjoint equations? I mean, would that be possible to do a joint sensitivity?
Non-twin equation?
Do a joint sensitivity analysis based on now that you have a solver that can cope with high dimensions.
So sorry, can I say again?
You have a solver now that can cope with pretty high dimensions theoretically for the for the state space for this chemical species.
Yes.
I mean, could you use this solver then to efficiently do a joint sensitivity analysis?
Yeah. So
Have you tried that?
I haven't. So I mean, what we do is just take the transpose of A and solve the same thing, right? Yeah. So numerically, what I'm doing is just take a transpose of A, and as long as I can solve the forward equation, from the numeric point of view, I just take a transpose of that. So the difficulty or the problem I'm gonna have will be similar for the forward problem from the numerical level. So this is a joint problem, yeah. So I didn't do that in practice yet. So yeah. So it's good to see how it works. But I assume if I solve the adjoint problem, all the behavior will be very similar to the solution of the forward problem.
That's what I would think too. Yeah, I think so.
Yeah.
Okay, I think I would suggest to move on the discussion next to tea and coffee. So let's thank Shuohao again.